Okay, hello, my name is Eltzschig, and let's talk today about writing sustainable software, the how and the what. And let's start with things first. You can see all the questions we are asking here in the talk and also the code examples in this GitHub repository. I will also add this at the end of the last slide, this link. And also when you click on my profile from Meeting C++, you will also see this link, and then you can check out the slides later and also questions, code examples, and so on. So who am I? I'm a C++ developer who works for Eltzschig or on Eltzschig, which is an open source inter-process communication framework for safety critical system. What this means is in the end, let's say you have a car with a lot of sensors, and these sensors have to communicate. For instance, a radio has to communicate to a brake that there is a tree coming, and therefore it has to do an emergency brake, and this communication is done via Eltzschig. Eltzschig is written in C++, and is also open source and available via GitHub. And since we are a framework for a safety critical system, we come with some restrictions. For instance, we are not allowed to use a heap because we have to guarantee always that there is memory available if something needs to be sent. We are not allowed to have undefined behavior, and sadly also no exceptions. And inside of Eltzschig, we have also the Eltzschig soup that the Eltzschig stands on. And these are STL types like optional, vector, string, expected, and so on, all implemented in C++14. But again, for a safety critical system, so again, no heap, no exceptions, and so on. And why I'm here is Eltzschig is software which is running on machines and cars, which sooner or later will be involved in accidents, not by fault of the software, but maybe some kind of other external incident. And we have to really make sure that our software is never the cause of such an incident, and therefore we have to really ensure the software quality. And sometimes in my field, some have maybe the misconception that when you certify a software, it's automatically safe. But this is not the case. You have to make the software first safe, and then you certify it, and then you can really say you have done everything to ensure the software quality. And when I took a look, I think in the last months, over the pull request we received, and then I just asked myself, maybe we can improve the code quality of our own commits and all of our contributors by just asking the right questions. So, because something which you want to never see in a safety critical environment is some statement like, when I wrote this, only God and I understood what I was doing. Now God only knows. This is a quotation from Karl Weierstrass. Maybe it's a German mathematician, but when I researched it on the internet, it was not really known where it come from. And this talks presents some ideas and concepts which are important in our safety context, but I think they can also apply to many other domains, because what we also all care for is a stable software where we as a developer do not have to do overtime or some crunching. We just write something and it works out of the box, hopefully. And maybe we can inspire each other. So here's also some kind of key difference when you take a look at C++ in a safety critical environment. In C++ in general, you say what you don't use, you don't pay for, you want to have maximum performance. But in a safety critical system, when you are driving in a car or flying in a plane, you do not want to have this. You want to say safety first, performance second. This does not mean that we do not care about performance. Performance is also very important. But if you have the choice between undefined behavior and maximum performance, or you have defined behavior, it costs a little bit of performance, but you have safety guaranteed with this, then we go for safety. So, and here what I explained, sooner or later, the products which are running our software will be involved in some accidents, and we have to make sure that our software is not the cause. And here's also something, Murphy's Law, for instance. When you take a look at this, it states everything that can happen will happen. And here, when you take a look at bugs, for instance, you can say, if the code base is large enough, every possible bug will sooner or later will be somewhere happen. And we have static code analysis tools to reduce the probability of this, but it's never zero. And therefore, the question is, can we do something about this? And the first thing we also have to be aware is, when you write software, it's like painting a picture. This is especially something which I realized for big companies. Big companies like to plan everything from the beginning to the end, but this is not possible for a software project, for instance. A software project starts mostly with some kind of idea. With Eltzschig, it started with like, we want to have some kind of software where we can establish some kind of communication between applications in a safety critical environment. And then we discovered new use cases and new features we would like to have. And then it grew, and we didn't foresee all the abilities and ideas and features we had in this product right from the beginning. But in the companies, they like to plan software projects like an architect will build the bridge, because they think, okay, if you plan it wrongly, you have to demolish the whole bridge, and yeah, then you end with something like this. Here, this is a bridge was built, but not over the wrong river. A rainfall occurred, and then the riverbed changed. And this is, of course, expensive to change. But if you write a software carefully, I think such changes will never happen, or that you can, in such a situation, that you cannot change the software project or the features anymore. When you write clean code, you can adapt this very well. And then it's like painting a sketch. This is a pencil sketch of a moose from me. And here I started also with the idea, I want to draw a moose. I have no idea if it's laughing or crying or somehow weird. And then with the new features, it's like painting. Then you add some trees at a hill, some kind of sunlight or atmosphere or a moon, whatever you want to have, add the colors. And these are all the features which are coming in, and you adapt this. Maybe you override something and so on. So now this is the questions we will look at. The first one, is the design over abstracted? Again, since it's like painting a picture, you have to realize that design is always incomplete, and you cannot foresee all the features which you like to have. And a software is like a living organism. When you write the code, you will realize that there are new things you can adapt or apply the software. And therefore, just consider the basic use case and start with this. But the beginner mistake is that you create a new UML diagram with a lot of classes and enterprise architect, and you try to cover all the stuff and to try to make it as abstract and extendable as possible. But then, for instance, enterprise architect does not verify if the code has circular dependencies, which makes it more or less impossible to implement, or you use some dirty tricks with pointers and pimple and so on to realize this code. And this is a typical beginner mistake. And how to avoid this over abstraction is very simplistic. Do small cycles. Have your one basic use case. In our case, it was establish a very basic communication, send a message, hello world message, and receive it on the other side, print it out. And you can do this, for instance, you can do this with planned UML or with enterprise architect. But my favorite method is here, just declare some empty classes with empty implementations. But you declare all the methods, then you can compile this actually, and you see, for instance, that the code you are designing is somehow working. You do not only have to fill the implementation then, and then you can use Doxygen, for instance, to generate a class diagram, can review it, can maybe do some cycles here, and then you have the most basic use case working, and can then extend the design. And this is some circle which always runs like this. You create your design element. In a basic use case, for instance, when we write some kind of communication software, we have a sender and a receiver. We create this design element. We create some empty methods. We compile the stuff so that we say, okay, the header is fine. Then we implement the basic use case, and then we start again. So, and here is some philosophical idea which came up around our colleagues is, in the Middle Ages, you had the jester or the professional fool. It was not only for entertaining the people, but also sometimes for the lawmakers. The professional fool read the laws from the lawmakers, and if the professional fool could explain the intention of the law to the lawmakers as they intended, the law was passed. Otherwise, the law could not be understood by the common people, and therefore has to be rewritten. And now the question is, can we adapt this idea somehow for our newly developed API, for instance? There, the idea would be we have a colleague which is a good developer, but not so familiar with the product we are currently working on, with all the details and side effects and so on. And then we just say, here we have two classes, for instance, for you. The basic use case is the following thing. Can you implement an example? And here, for instance, we also state that the developer does not get any kind of documentation, because as Björn Stustrup states, the compiler doesn't read comments, and neither do I. And here the idea is, can the API be used intuitively right? If not, we maybe have to adapt the API so that it can, because in the end, when a developer starts working with such a framework, they are maybe under pressure, have a 60-hour work week, and maybe they do not have the time to really read the documents carefully, and therefore easy to use API is extremely important. So now the question, is this API easy to use and hard to misuse? Let's take a look at this bad API. Here we have a receiver, and this receiver has a constructor, init method, add connection, connect, and disconnect. And with these methods, there comes a lot of contract. First of all, the init has to be called first. After init is called, we can add some connections. After we added some connections, we can call connect. And when we are connected, we can again call disconnect, but only after we called connect. And init can be called only once. Therefore, if you do not read the documentation carefully, you are doomed to misuse it. And now let's say we would give this our colleague and say, here, this is a receiver. You can here add some connections, disconnect it, and so on. Just use it. You maybe think of something like this. Yeah, first I want to connect the receiver, then I add some connections, then I disconnect it again, and then maybe assumes, yeah, maybe it's something like a placement new or whatever, or it resets the object. So I just call init and then I add some connections again, because maybe I am assuming that the connections are then resetted and then I start again. And here we are violating the contract all over the place. And when you are under time pressure, this can lead to extremely weird behavior. How can we do better? So let's take a look at the object, and we realize that it actually has 3 states. The first state is before init was called, we just constructed it. Then the second state is after we called init, then we have the ability to connect or add connections. And then the third state is when it's connected. And when we would be at a Rust conference, everyone would now scream and say, yeah, it's a type state pattern, but we are the C++ conference, and therefore, what is a type state pattern? So the type state pattern is we encode the runtime state in its compile time interface. This means that depending on the state, the interface is different, and therefore by the compiler can warn us with, or can hint us what kind of methods we should use. And it would look something like this when we implement this. The first element or class we would require is receiver state. This would be the class where all the member variables these following objects would share. Then we have a class called receiver connected. Here we can just call disconnect, because as soon as we are in the connected state, we are only allowed to disconnect according to the contract. And we have a constructor where we retrieve the ownership of a unique pointer of the receiver state so that we now own the object or the state. Then we have a second class called receiver initialized. Here we again retrieve the unique pointer, the ownership of the members, and we can add connections or we can connect, depending on what we want to do. And when we connect, we return the receiver connect state and then can work with this. And the initial class, initial state would be receiver, where we can just call init and then retrieve a receiver initialized object. And the receiver state is depending on which state or in which class we are, is then moved to the according class. And then when you take a look how one could use this, it would look like this. Then you just say receiver.init.add connection, and then you connect. And let's say, for instance, now our developer would like to misuse this. It's impossible, because it would lead to a compile time error. Because you cannot call init twice, you cannot call add connection after you called connect, and you are only able to disconnect after you called connected. And this is a design or an idea which is known as design by contract. This means the contract is enforced via the interface. And now the most awesome thing is that your IDE will tell you how to use this object, because when you start receiver and then press dot, you get only one suggestion, and this is init. After this, you complete it, you have 2 options, add connections or connect. Therefore, you do not need to read some kind of documentation. You can just use this object right away, only correctly. And yeah, this is quite nice. But it's also cumbersome when you have you want to move the state transition in multiple functions. And you have also some other problems. For instance, here's a hidden move inside. Let's try to take a look at this and try to fix this. So let's say first we want to use this API and move some kind of state transitions into different functions. Therefore, you can say something like this: we create our receiver. Then with this, we create our receiver initialized object, and when we say receiver init, then we add some connections, initial, and then we connect the whole receiver, and after some time we can disconnect it. But what we have here is the thing is a little bit cumbersome to use, and the other thing is in these functions here, for instance, here is a hidden transition of ownership. The unique pointer to the receiver state is moved from the receiver to receiver initialized, and this is not, the compiler is not really aware of this, and the user is also not aware of this. And then when you write something like this, you have undefined behavior. So how can we fix it? So the first idea would be to just introduce static methods which are called disconnect, connect, and init, which we had before, and here we move the previous state into this new object. Therefore, it's completely clear for the user and also for the reviewer that now the ownership has changed and is now on a different state. And when you take a look at the code, it looks like this. We have a receiver initialized. Then we have to move the initial receiver into the receiver init method. And then we can add some connections, and then we can continue and connect the receiver when we move the receiver initialized object inside this connect static method. And then we can call disconnect and so on. And now the ownership is clear to the reviewer and also clear for the compiler. Then we now write something like this here. We get a use after move warning. For instance, I tried it with the current compiler. It works perfectly. With GCC, it has at the moment still some problems. But nevertheless, okay. But let's say I want to ensure that these methods are all chained together because I wanted to use them like this. I can do the following trick. I can make these methods here, the init and the add connection, I can change them to R value methods. This means they can only be called if the underlying object is an R value. Therefore, you cannot store the receive in some kind of variable and then call the method. It has to always be an R value. You can do this nevertheless and try to misuse it, but it's very easy to spot a spot. Then it would look like this. He would just call stud move, create an R value out of receive initialized to just call the method add connection, which would be just wrong, and it's easy to spot in a review. Okay. Next question. Can we reduce the error handling? Again, let's stick to the receiver. And since we have here 4 methods which can be misused, and misuse means here they are just called in the wrong order, we have to inform the user that the call actually was successful. And sometimes the user really doesn't know or is unsure, and maybe say, okay, I have no idea what to do here when it fails. Therefore, I just propagate the arrow up a layer to the public API and so on. And if you follow this kind of behavior, you have a lot of unnecessary error handling in the public API, which can just clutter the code with unnecessary tests and so on. Just take a look at this, for instance. Let's say, for instance, we want to also have the ability to remove connections. Therefore, we can add a connection, and then we have some kind of comment which states it returns true when the connection existed and was removed, otherwise false. And now you review code and see something like this. You see here that when the remove connection has failed, we have to maybe do some stuff. But here in the end, the contract is, after you called remove connection, the connection is no longer present in the receiver. If it existed before, it's irrelevant because the contract is either way fulfilled. And here something would be, for instance, here we can really omit the error handling completely because it's nonsense, because the contract is fulfilled either way. But if you want to make sure, for instance, if some kind of connection is present in the receiver, you can add a certain method for this, like is connection present or something like this, which then returns the bool to just reduce the error handling, because it really accumulates and multiplies in the public API, and you have thousands of lines of code and thousands of lines of unit testing, because you have to handle all these kind of errors and have to really test if the object is behaving correctly in these error cases. Just take a look at this comparison. We have either the left side where we just say receiver init, add connection, and connect, or we just have the right hand side and we do not use such a kind of contract by design approach. And with every method, we have the possibility that the method is failing, and therefore we have to do some kind of cleanup code, have to return some kind of error code, and then in the public API, some poor developer has to handle all these errors, which in the end are not really necessary. And then in the end, when you write safety critical software, you have to also test this. This means also MCDC testing. Therefore, you have to really test every branch if that the code behaves correctly. And these are thousands of lines of code. And this, with this additional lines of code, also the probability for bugs increases. So next thing is this API easy to use? The concurrent case. Let's say we are very smart and we wrote a perfect thread-safe integer vector, which is log-free and has all the features and has no bugs whatsoever. And now we just take a look at those two methods. The square operator to just to access an element at a certain position and to check if the thread-safe integer vector is empty. And now someone uses our vector and writes code like this. Whenever my vector is empty, I want to just print out the first element. In a single-threaded case, this is perfectly fine. But in a multi-threaded case, we have here multiple issues. The first thing is, as soon as we acquire the information that the vector is empty, our operating system can interrupt us for any arbitrary time. Another thread can swoop in and say, oh, I don't like this vector anymore. I just clean it completely. And then it's empty again, and you access an element which is no longer valid. And the next thing is, again, this vector itself is thread safe, but maybe here in this case, it has no responsibility to make thread safe integers. The integer itself is again not thread safe. Then when you here access a reference to the underlying integer, which the thread safe integer vector is managing, it's possible that someone writes data into the integer while you're reading it. And then you have again race condition and data races. Therefore, here's the question is, when you're working on a concurrent API, is it useful that it looks like a non-concurrent API? Sometimes it's maybe useful to just dismiss the completely standard API and go a completely different approach, a functional approach. How would it look like? For instance, you know for each from the STL. For each is from algorithm where you can just iterate over a range and then you can do something with the elements in that range. Or let's say we have a for method which does exactly the same thing, but only for one specific position. And then we can write code like this. For index null, if the index null is present, please just print it out. Otherwise, don't do anything. And with this functional approach, it's impossible for the user to misuse this in this particular case. For instance, here also what comes in with when you provide empty and an access operator for the vector, you have to also introduce now as a user artificially another mutex to just make sure that these two operations, the empty and the access of the element, that you can access this thread safe. And then you just somehow circumvented the cool features of the thread safe integer log-free vector and have introduced another mutex. So why not just get rid of this error and introduce a functional API? Another thing, a use case of a vector is that you maybe want to add an element and later you do not care anymore for this element. Then you do something like vector findif, then you get an iterator and then you remove the element at this position. But when you have, again, a thread-safe integer vector, it's possible that you find the element. After you have found the element, someone else in a different thread is changing the vector, and then your iterator is no longer valid. Therefore, why not use here again a functional API where you just say, for instance, with pushback, you add an element and you get the position of the value. It can help you, and then in the remove if to improve the performance. When you say, okay, the last known position of my element was this here, I give you a hint, like for instance with the map where you can insert and provide a hint, and then you have here a callable which returns true if this is the element you are looking for, and then it's removed. It's similar to the std remove. And here we have a functional API which minimizes the misuse cases of a thread safe vector. And it's nearly impossible now to remove or add or change the vector in an unsafe way. Of course, you can still capture some variables here in the Lambda and can do some or can introduce some bugs, but the I think, in my opinion, the probabilities of bugs is reduced here with this functional approach. And here's something you have to keep in mind. When you create thread-safe constructs, you have always to face two challenges. The first challenge is to create the actual construct. And when you master that challenge, the second challenge is you have to design an API which allows the user to really use this construct in a thread-safe way. And when you now provide methods like empty, size, or an operator which returns a reference to an internal element, you make it extremely easy for the user to misuse this. You have to be really careful then as a user. You have to read the documentation, you have to really consider all the side effects which can happen here maybe to use this correctly. Why not provide a functional alternatives like when empty, do this please, or when size has this size, for instance, then do this please. Or like with the operator here, you can have the for methods. Next thing, does the name fit? This is something where the C++ developer or the developer in general have some kind of issue because it's hard to find the right name. And here I came up with some certain rules. The first thing is that a class should always reflect the purpose, as a class name or the struct name should always reflect the purpose of the object. For instance, if you have an object which has a particular role in a design pattern, for instance, you have a factory which produces receiver, it could be a receiver factory. Or if you, for instance, implement the visitor pattern, you can also use the names which are stated there and so on. They can, for instance, a receiver, visitor, whatever it does then. And if you say, okay, I cannot really provide here the purpose because the object has so many purposes, I cannot come up with a right name, then maybe it's an indicator to split the object up to come up with a better name. The next thing is, how could I name functions and methods? Yeah, they should reflect the task the function or the method is performing. And when you say, okay, I cannot redefine the task the method or the function is performing, and you require the words and or, maybe again, this is an indicator to split the function up. But it should not be a strict rule, but sometimes it really makes sense to have a little bit a bigger function when you write the first implementations of your first use case or you write a POC. You should not start with over abstraction. But when you try to finalize your design, harden your software, these are some kind of indications that you have to do. Here's maybe a bit of more refactoring and abstraction. And the variable name should reflect its content, what it's containing. For instance, here we have a sender, and the sender has a list of receivers. It could be the receiver list, for instance. And when you have problems with naming, maybe the cause is the design idea is not completely clear in your software. Maybe you were not aware that you're here using a factory, or that you could use here a visitor pattern, or that you here could use a facade pattern or a builder pattern or whatever. Also, sometimes a single responsibility principle is maybe broken, or the separations of concern. So maybe this helps to come up with better names. And also bad naming can lead to bugs, as we can see here. In Eltzschig, we implemented also STL types like string, but with the restriction, no heap, no everything resides on the stack. The capacity has to be known at compile time, and exceptions are not allowed. And we try to be as compatible as possible to the STL, but we renamed explicitly assign to unsafe assign. The reason here is that the reviewer should really know when one reviews the code that this string, which is provided an unsafe assign, has to be null terminated. If it's not null terminated, we have here a potential problem with memory issues. And therefore, with unsafe assign, it's something like a keyword which you see in the review or when you write code, okay, I have to pay attention here. But this is something which we do not have to do, for instance, when we are assigning another string to a string, because here we have guaranteed that everything is null terminated and we do not have the problems with the memory safety. If you would like to look at the implementation of the string, here's the link, or later on you can find it also in my GitHub repository. Can one produce readable code with this API? Let's say you review code and encounter this little method here. It has 5 booleans. They are nicely described. You can read them easily. It's a perfectly readable implementation. So from this side, you would say, okay, thumbs up, we can merge it. But now the question comes in, can I actually produce readable code with this API? And let's take a look at an example. We can, for instance, produce code like this. which is absolutely not readable because you see just random booleans, and when you later have to use such a piece of code, you have no idea what to do. And even then, when you just use your IDE and try to figure out what argument is standing for what, it's that you, for instance, see that the third or fourth argument is standing for do receive history or do print messages. Even then, you can make a mistake. Then you maybe say in a review, okay, you have to do better than this. You are not allowed to introduce magic numbers, and then you come up with an implementation like this, and this is still error prone. And this seemingly perfectly readable implementation, we have two bugs. The first thing is we state that we are using TCP, but actually we are not using TCP. And the second thing is that do not log messages and do print messages are switched here. And this is extremely hard to spot, but the solution is also very easy. Just use enums. And then you can write code like this. It's again very readable. The user has to write less code to produce readable code. And here also something kicks in. It's a strong type safety of C++. Let's say we would mix up here the order of some arguments, we would get a compile time error because these are different types, and with C++ comes strong type safety. And the next thing is enums are extendable. Booleans are not. Booleans have only the value true and false. But let's say, for instance, you want to extend the protocol, you would like to support TCP, UDP, and whatever kind of P you can think of. You can just add this to the protocol and have a list of nice protocols, and this is extendable. With Booleans, you have to rewrite the code and you have to change this API. Can the API be used without documentation? Let's assume, again, our good receiver now gets a constructor where we have these four arguments. We can set the history cache size, which means that we, when we connect, we receive the latest 10 samples, which were sent out in this connection, for instance. And whenever we receive something, we want to have that a certain callback is called. Also, the same thing is when we establish a connection, a certain callback is called. And the last thing is, should we acknowledge every sample which we receive to the sender? And these two arguments here are optional, which is described here in the documentation. But this API should also be usable without documentation, so that it clearly states to the user what is going on. Because when one sees just this API, one may think, okay, when I provide here an empty function, maybe an exception is thrown somewhere, or maybe I get some kind of error because it's not really stated. Do I have to really provide here some kind of callable or not? Because the function itself is nullable. But when we introduce here an optional around this, we say to the user, this is optional. You do not have to provide this. You can provide this. And this makes it clear for the user. It uses also the error handling, because maybe when you think, okay, this has to provide to, there has to be a callable provided. And when you create, again, an abstraction around the receiver, you want to make sure that the callable is always there and so on. And this makes the code future-proof and also provides additional insights for the reviewer. When you take a look, okay, now let's take a look at what bugs does an API allow. And we take a look at our callback. And let's say, for instance, we have the on-receive callback, and we just call it. And here we can easily throw an exception, for instance, when we use a stud function, but the stud function does not actually contain an object. The better way would be, for instance, when we call this object optional on a receive, and then the reviewer says, it's optional. We have to verify that this actually contains the value, and then we can call the stored functional. But we have here also some drawbacks. To rename every variable optional whatever is also some kind of counterproductive, because sometimes you just do some kind of code refactoring and you turn an optional into non-optional, and you forget to adjust the names, and then you have an inconsistency with the actual type and the name. Therefore, sometimes you have to verify or have to check out if it's suitable for your use case. But a cool new feature of C++ 23 will be the monadic optional. Let's say in the good old days, if C++ 17 and 20, we use an optional like this. We define here an optional value, and when it contains a value, we use a dereference operator and just print out the value. Otherwise, we do something else. But in the new cool world, we can use the functional approach and write and then. And this callable here is only called when the optional contains a value. Here you provide a reference to the underlying value of the optional, and then we just print it out again. Or else, if there's nothing contained, we do nothing. And when we only use this API, it's extremely hard to use misuse an optional or to run into any kind of bugs. Just for instance, think of other types like a unique pointer or shared pointer. Maybe we should, in a safety environment, say, okay, we try to restrict the access to such types only via a functional approach. This is maybe not the perfect way to maximize your performance in your application, but it's maybe the best way to minimize the probability for bugs in your code. Just take a look at this. You have here a unique pointer, and let's say you would have here also a mnemonic approach and could write just and then whenever the integer pointer contains actually a value, you just print it out. Otherwise, you do nothing, and then you have clear defined behavior. And when you, for instance, this is very strict and maybe also not for a safety critical environment as adjustable, but just for instance, when you would forbid to use the arrow or the star operator, then you cannot really misuse this unique pointer anymore. Okay, you can of course capture something in the lambda and then transmit the address of the inside value out and then do crazy stuff, but this is cumbersome and I would state easy to use and hard to misuse. And here the counterpart is you have a classic unique pointer and then you can easily access it without having any kind of value, and then again you have undefined behavior. And now let's apply this, for instance, to our callback. Let's say, for instance, we have still our optional on receive callback, and we here on this line call it, maybe it doesn't contain a value, and then we have again undefined behavior. But when we would have, for instance, a functional approach, we could say, okay, if the optional on receive contains something, then please call the underlying callable. But here I assume that the callable, the stood function, is never null. And it makes sense, for instance, that you try to, when you say you have an object which is nullable, to enclose it in an optional and try to avoid to use really the nullability of a type because it can lead to bugs. And if you want to take a look at an optional which already supports such an API, you can also again look here at Recursive where such optional is implemented. Is the API easy to use? Here, let's assume again our receiver with our 4 arguments, the history cache size, on receive, on a connection, and acknowledge. Get some kind of default values because it makes stuff easier and it's easier for the user to create a receiver. And therefore, we come up with some kind of default values like 10 because on receive and on connection are optional. Therefore, we say, okay, in the beginning, we do not need to set anything. And every time we receive a package, we send it out and acknowledge. And now the user comes to us and say, okay, I would like to change the first and the last argument. One approach would be we just try to change the API and overload the constructor so that we have one constructor which starts with the history cache size and one constructor starts with acknowledge, and then we have 10 variations of constructors so that every kind of optional use case and so on is covered. And this is just a mess and extremely error prone. And we can actually do much better. The first thing we have to do is we just pack all these arguments into a struct. This is something which I would recommend whenever you have a functional method which contains more than 2 arguments, let's say, just to make it more readable. It's not always usable or useful, but this is something you should keep in your mind. And now let's say we have our history cache size, we assign it again 10 and all the default values we had before. And now we use it in our constructor. And how does it help us? Now we can use the C++20 feature aggregate initialization and only set the first and the last argument. How does it work? We use just the uniform initialization. And here, for instance, we have in this example a struct called struct name, and it has 2 members, or maybe it has 5 members. And we just want to initialize a member name and another member name with value 1 and value 2. And this is how it looks like. And when you write and apply this to our constructor and write code, it would look like this. You would state here, we have a receiver, my receiver. we construct the receiver info and state that the history cache size has to be 20, and we do not want to send an acknowledge. And we do a comparison. We see here on the right side, we have again magic numbers. It's not completely readable because you have no idea, is the first null up now for the on receive or for the on connection callback. And this is more or less readable. You know what it's doing, but the other arguments are somehow a little bit, you have no idea. And here again, the user has to create some variables to avoid the magic numbers and to make it really readable. Or you use a different approach with the C++20 aggregate initialization and just state here explicitly the history cache size is 20 and acknowledge yes, we want to discard it. And this improves the readability a lot. Okay, is the task the code performs clear? Again, we stay at our good old receiver. And let's say someone says, yeah, my typical use case is I either have one connection, and whenever I have this connection that I want, that the receiver in the constructor that I can add this connection, and then the receiver connects automatically because it makes life so much easier for me. Or the other use case is I have a bunch of connections, then I want to add all these connections to the receiver, but I do not want that the connection that the receiver connects automatically. I just want to add these connections, maybe later add some more connections and so on. And then you write a receiver which looks like this in the interface, and you write code like this. The only difference here is one curly brace, which changes the behavior completely. Here in this case, we connect automatically, and when we add a curly brace, we do not connect automatically. And here we have universal initializer list, which initializes a vector of connections, and we do not connect. This is not readable at all, and this is extremely bug prone. Can we do better here? And here, this is a trick I learned from the implementation of the stud variant. Here they have a trick. They define two structs. In our case, we would define two structs called connect on creation and add connections only, so that the user knows the intention of the constructor. And so that we do not have any runtime overhead, we just create some const expressions and say here connect on creation and add connections only, and add these two to the constructor. We have one constructor where you say connect on creation, and we have a different constructor where you say add connections only. And when we now write code, we clearly see what the constructor does. Either it just connects on creation, or it just adds the connections only and does not connect. And when you compare it to the readability of the right side, you see a clear improvement. And it makes the code much more readable and reduces the amount of bugs because you clearly see the intention and the idea behind this. So, something else here. When you have the possibility, it's not always possible, but the best thing to do in such cases would be not to introduce such a struct, to just introduce factory methods. Here, for instance, we do the following. We have a receiver and create two static methods called create and connect and create and add connections. They return an optional. In our use case in i6, we have also an expected on our hands. Therefore, we return here an expected, which provides also the an arrow value to the user so that the user knows what's going on when the receiver could not be created. And here we just say, okay, that's a connection, create and connect, and it's very readable, and had also the advantage that you can do some better error handling, and also you improve the testability because you can here inject also mocks. Ownership and lifetime, do we use RAI? Let's say during a code review encounter pairs like this, add something or remove something, or create something and destroy something, attach, detach, allocate free, open, close. And maybe there are some even more indicators. And whenever you encounter such an indicator in some kind of API, you should think of RAI. RAI means resource acquisition is initialization. This means that we bind the resource's lifetime to the object's lifetime. Very classic examples are the unique pointer and shared pointer. And let's say we have here open and close. We have open a file and close a file. Then the file is our resource. And when we return some kind of unique pointer or whatever, we bind this return value to the resource lifetime. And whenever this object goes out of scope, the resource is closed. And now let's apply this. And we would like to have a callback in our receiver. And whenever the receiver receives a message, we have a sender object, and the sender just forwards the message and sends it out to the next receiver, for instance. And we could implement this like this. We attach an on receive callback and say, okay, whenever some user would like to have some kind of callback attached here, you can use this method. And when you are done with the callback, you can just remove the callback and provide me the callback ID, which I provided to you when you attach the callback. And then someone will say, okay, now I create my sender. This sender has already a callback ID for the receiver, and we attach here our receive callback. And here inside we state, okay, this callback is called whenever the receiver receives a message. Therefore, we acquire here the message in this line, and then we send it out. And then we are done with it, with everything, and we forget here to call remove callback before it's going out of scope, because maybe the developer who used my sender in some kind of other method wasn't aware that he has to do such or that they have to do such a cleanup. And we have here a dangling reference because my sender is no longer valid after it's going out of scope, but attached on receive callback, the receive callback is again called when some message is received, and we access my sender, and then we have a dangling reference. And with Rye, we can get rid of this little problem. For instance, the unique pointer can be used in combination with a custom deleter. Instead of returning just the callback ID, let's pack the callback ID into a unique pointer and into with a custom deleter. This would be then the return value of the method. And this is how we would create this return value. We would get from somewhere else the callback ID, would create here the callback ID on the heap, initialize it with the value wherever we have acquired it. And then we would state here, we capture this, and whenever the unique pointer goes out of scope, we first call remove callback. Therefore, the callback is gone, it's cleaned up cleanly, and then we delete again the callback ID. And when we now use the same thing again, we do not change the code at all. We just have to change here the underlying type because it's not a callback ID underscore T. It's now a unique pointer with a custom deleter which contains this callback. And when the sender goes out of scope, callback ID goes out of scope, and everything is magically cleaned up. And this is another way to reduce bugs. And whenever you can, just use Rye, because then you have a clear ownership and a clear lifetime of your resources. But it also again comes with a drawback. Let's say our receiver is again stored in a vector, and this receiver can be moved or copied. And when we capture this pointer here, then it can happen when the receiver is moved that this pointer is no longer valid or is pointing to the wrong object or a copy of the object, and therefore the wrong callback is removed or only partially removed. Therefore, whenever you use the technique with a unique pointer with a custom deleter, you have to either make sure that copy and move operations are deleted, or you have to make sure that while you're using this approach, you do not copy or move the object anymore, or the best way would be to not use a unique pointer to write a more complex class yourself, where whenever the unique pointer or the callback ID, which is then provided to the user, and the underlying object is moved, then the callback ID is informed that the underlying object where you deaddressed and call remove callback is now moved, and that this pointer has to be updated. Is the code expandable? Let's say now we take a look at the sender. A sender is a simplistic class where we just say we can attach a bunch of receivers, and then we can send a message to those receivers, and we want to deliver these messages with a method called deliver. And to do this, we want to have a class render which contains a vector of all the receivers called receivers, and here are the shared pointers to the receivers, and then we can do the following: attach a bunch of receivers, and whenever you want, we can send out a message to all the receivers, and then the receiver can handle the message how they would like. And the first thing is, when you want to implement this, you maybe think, okay, just write some kind of abstract base class. We have to define there that we have to implement the deliver method, or we maybe provide a default implementation, either an abstract method or some kind of default implementation. And then you can inherit from this receiver base class and can write all the receivers you would like. But let's assume you cannot do this. You do not want to inherit from receiver because this receiver base class has a lot of overhead, or in our particular case, for instance, because we are working across process boundaries, we are not allowed to use vtables. And then you can sit back and say, okay, what's actually object-oriented programming? Object-oriented programming means that objects are communicating via messages. So when you think of it in an abstract way, in the end, in object-oriented programming, every object is somehow a sender or a receiver, because you will receive some message from another object. This is by calling the method, or you're sending out a message by calling a method of some object. And can we do something like, can get rid of inheritance and attach any receiver which has a deliver method? Okay, we could now say, okay, we just use some kind of template inheritance, but then the question is, okay, what do we store here in the vector of the receivers? So the answer is nice and quick. We change the attach method a little bit of the sender and make it a template and say here, we have a receiver type and we can attach anything you would like as long as it's coming inside of a shared pointer, and then you provide us the receiver. And what we are doing here is, instead of storing the object itself in our vector, we store the task, the message we would like to send, the way the message should be sent. And this means we are capturing here the receiver inside of this lambda. This means we get a copy of this inside here. And whenever we want to send out a message, we just say, okay, deliver the message, and out it goes. And here we have a nice way to close the gap between compile time inheritance and runtime, and compile time and runtime. Normally, you have something like this. Let's say you want to go or close the gap between compile time and runtime. You have multiple types, for instance, and then you have a big switch case statement, and you have to decide what kind of method or what to do with this particular case and so on. But here, everything is covered via the callable in the function, because this is just a copy of this. You can copy any kind of object in there, and then you can call deliver on any object which just has a deliver method. This concludes my talk. Again, if you have any questions, or you want to see more source code or something like this, but also if you have questions, maybe 1 or 2 days from now, just go here into this repository, create an issue, or pull a request if you think there are some questions missing, or you want to add some kind of code examples or something like this. Just go there, and now I'm open for questions.
Thanks, Christian, for the talk. We already have some questions. I'm not sure if you are seeing the question slides. Yes, yes.
Okay, I see here. I just read the question. Christian Kaiser asks, if you are using C++20 in productive code, do you know of any safety qualified compiler? We do not use C++20 in productive code. We use C++14 in productive code. But what we try to do is to take a look at all the cool stuff from C++20 and 23 and implement this in C++14. At the moment, I think the latest C++ standard, we have a certified compiler for a C++14 with QNX. Jella, are you using C++20 in productive code, or are its features? It is okay. We use the features of C++20, for instance, with designated initializers. You actually can use this with GCC or with QCC, the certified version of the QNX GCC compiler. But you have some restrictions. For instance, if you have 4 members, you cannot use them in an arbitrary order. You have to always follow the order as they were declared. And you cannot skip any members. You have to really define all the members. But still, it's much more readable than just using it better. Well, okay, slide 72. What would you suggest to address the risk that the user will mix up the 2 optional callbacks? Slide 72. Okay, here the solution would be to use designated initializers, or there is some kind of pattern. I can add this to the repository. In Eltzschig, we came up with a Haskell pattern. It's called MuType pattern, where we, for instance, state or the idea was the following. Let's say, for instance, you have multiple FIFOs and they are returning some kind of indices, but you do not want to mix them up, the indices, so that you use a wrong indice for the wrong FIFO. And therefore, we used again the type safety of C++ and created own types for all the indices, and we used the new type pattern for this. And this is in the end a kind of bunch of template classes where you can just state what kind of underlying type this is, like integer, for instance. And here in this case, it would be a std function or an optional std function. Then you can state, should it be copyable, movable, and so on. And then you have individual type for on receive and on connection. And when you then mix them up, you get a compile time error. Could you elaborate on undefined behavior not being allowed? Does your compiler define the behavior, for example, integer overflow? What happens when you do it? Undefined behavior, do you abort? Thanks. Okay. Undefined behavior, our compiler behaves like a normal C++ compiler. Therefore, when the C++ standard states, yeah, this is undefined behavior, yes, then we have undefined behavior there. But our software, which we deliver, we do not want to have undefined behavior. Therefore, what we do is either we wrap the constructs up which C++ delivers us and get rid of the undefined behavior, for instance, with some kind of more extensive error handling, or we, in the end, we implement the STL constructs ourselves because we are restricted to C++ 14, but we would like to use an optional, we would like to use an expected or whatever, or variant, for instance, whatever cool feature we would like to have. And yeah, that's the way we go. Okay, early slides. The pattern used unique pointer, but in safety environments you don't have heap. This is correct. This was just an example to illustrate the behavior. And we have in our safety environment, we actually have implemented unique pointers ourselves, but it works a little bit differently. We have a bucket allocator, and this bucket allocator returns not pointer, it returns pointers packed inside of unique pointer. Therefore, with this bucket allocator, when you allocate something, you get a unique pointer or a shared pointer out of it, and then you can work with it and do not use the heap. Okay, then the next one, the lambda requires a lock in the thread safe integer vector and chooses a high deadlock risk as its arbitrary user code. Let's go back to the vector. I have no idea where was the slide. Oh, I can previously, okay. Okay, I think you mean this, for instance, or the other lambdas. The first thing is, let's say it's extremely hard to create a lock-free vector which using such of kind of behavior. Therefore, you are right, you have to use a mutex inside of the thread safe vector, but it's encapsulated inside of the vector. The next thing that this introduces a high risk of a deadlock because someone else could here do some crazy stuff. For instance, we could capture here something, and when inside of the thread safe vector, we could again do something with the vector and we push back another element, and then we have a lock which again runs into a lock, and then we have the deadlock we are mentioning. But here we can first hand we can use recursive mutex to get rid of this problem. And let's say, for instance, you would do the following here. You introduce here a lambda which it creates a new thread inside of the lambda, which again then does a pushback and then waits for the pushback to complete. And this is then during the lock. Even then, the recursive mutex will not help you. But here, I would say this would be a misuse case. This is also something we have to face here also in reviews. I have no idea how to get rid of this, and this is a problem we have to be aware, we have to take care of. But I would argue that using this in this manner, in my opinion, improves safe usage of a thread safe vector to use it functional, but it comes with drawbacks and you have to be still very carefully. The next question. Could you repeat why you can't use heap in this environment? Use an alternative. How do you allocate memory? Okay. We are not allowed to use heap because we have to guarantee at any given point that, for instance, when some camera image comes in and requires 1 megabyte of memory, that this 1 megabyte of memory is available. Let's say we would use the heap, and let's say we have 10 megabytes of heap, And we would have 10 megabytes of very fragmented heap. This means we do not have one piece of memory which has the size of 1 megabyte. We have a lot of pieces which have the size of 100 bytes to 100 kilobytes, for instance. And now we go to the allocator and say, okay, we have 5 megabytes left, but extremely fragmented. Therefore, we cannot get this camera image anymore, or can reserve memory for this camera image anymore. And then we just fail. And this should never happen in a safety critical system, because when your camera detects a tree and you have to break, then this memory has to be available. Our alternative is we allocate everything on the stack or in the data segment, and therefore we have a bucket allocator. And currently we are implementing a more sophisticated kind of allocator. The bucket allocator, in the end, you just state, okay, I want to have 100 memory samples with a size of 1 kilobyte, 100 memory samples with the size of 10 megabytes, 100 memory samples of a given size, and then these are stored in buckets, and whenever a user comes, he can get a memory sample from this particular bucket, and we can guarantee then that these buckets are always the samples available which were configured, for instance, by the software architect, and this is how we allocate memory. Next thing, slide 35. Is it not hiding errors when a remove connection does not remove a connection? The user possibly had the wrong impression that the connection existed. Yeah, one could say this, and this is actually something where we had a very nice discussion on GitHub about exactly this behavior. Slide 35. And the conclusion was actually, yes, maybe it can hide some kind of error, but here we wanted to make sure, for instance, if you want to make sure and you see this as an error that remove connection when you call it, but the connection was never added, we have to add another method to state, is connection available? If so, please remove it. And the problem here was actually when we reviewed code like this and we said, okay, remove connection, it failed, the connection is still available. What do we do now? What the hell, and what's going on? And it led to a lot of false impressions, and it was just used intuitively wrong, the code here. Then the error handler and then terminate was called because we thought, okay, something is really broken here and we have no idea what's happening. And then we read the documentation that, okay, yeah, it's just an informative Boolean. And therefore we said, okay, we split this up. We have a method called is connection connected or is connection available? And then we act on this. Why choose C++ for safety critical environments at all? It's not memory safe. It's very easy to accidentally trigger undefined behavior. There exist alternatives that are low level and performant as C++ and don't suffer from these issues. I think you are meaning Rust, and I'm on your side. I think also that for safety critical systems, Rust is maybe the future, but I will not give up on C++. I think we can a lot learn from Rust, and maybe C++ develops in the right direction, and then we are compatible or compatible again. Okay.
I think Christian answered all questions. I would like to thank Christian for this really great talk. And yeah, I think since at least the last question got a lot of interest here with 7 upvotes, maybe I can invite you to the launch. Where there is a special place for track C, where we can discuss further on Rust and safety critical and all the other topics, of course, of this great talks. Maybe more on the great talk and less about Rust, since this is a C++ conference. Yeah. Okay, then thank you very much, and thanks for having me here. I enjoyed it a lot, and see you there in the lounge.